Is it finally back online? Am I finally back online? Am I alive? Or is this just an illusion? I don't know. I don't know, no, no. Na 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 na. Na 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 na. Na 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 na. Hold on, not this. No. Why was it? Why are the order weird? Okay. No, that's not what I'm looking for. Computer science technology. Computer science for beginner. Oh, that's an hour long. That's actually pretty short. Computer science explained in 17 seconds. What is computer science? Wait, I do have a Khan Academy. I have to find youngsters. KhanAcademy.org. Looking. Signing in. Why is it taking so long? Ba 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 ho. Ba ba da ba 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 da ba da ba ba da ba da ba ba da ba da ba. Mana mana mo mana mana mo. Mana mana mo mana mana mo. Starting with the video first. I/O input output CPU computer computation unit. Can I move this door here? Not yet.
Device because data goes both in and out. So the relationship between these three parts, the CPU, the memory, and the I/O devices, is that the CPU is in control. The CPU does its job by reading instructions found in memory, and those instructions may tell the CPU to send instructions to input-output devices, effectively telling those input-output devices what to do. While the CPU will not execute instructions directly from an input-output device, typically what happens is that programs are loaded from a stored file, like say on a hard drive, then copied into memory, and then the CPU executes them.
Hold on, I want to try something. I forgot I have this. I think what's the command? Auto task. Okay, so the instruction is timer start. Configure timer go 10. Changes the timer go to 10. Timer cycle 5. Changes the. See, this is why it bugs me. Like, oh, okay. Dang, why can't I add a new line in the code message? Okay, so there's timer start, timer go, timer cycle. Use the current cycle to 5. Okay. Timer skip, either work or break. Timer 15 or 15. You just set time from dollar. Well, review will be fairly easy, not gonna lie. Okay. So timer pause, timer reset, or timer clear. So I'm gonna use timer. What is it? 4 hours. 140. Wait. Timer 20 minutes. Okay. Hold on. Where is my Pomodoro timer? Do I not have my timer with me? Oh, I did not. Interesting. Let's see, it's probably processors. Messages. There we go. Okay. And this side. Oh, is there no subtitle for this one? I didn't know that. Let's see, that should also be. I don't remember what's that. Oh, display capture. Nope. What was it? I forgot what it was. On the one. Okay. Bum 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 bum. Nice! Looking so pretty. I love it. And another screen just clutter. Yeah.
That program in memory. So in a sense, CPUs do execute instructions off of input-output devices, they just don't do so directly.
Hold on. What is going on? Why isn't my Pomodoro timer working? These? Should be the same one. Why is it not working? Odd.
The reason for this, as we'll discuss later, mainly has to do with performance. The CPU typically can read data from memory much faster than it can read from input-output devices.
Oh, was I supposed to turn on my timer? Timer? Timer enable? Wait, what? Timer enable Twitter? Huh? Twitter timer not fine. Now what am I using here? I have absolutely no idea. Oh well.
Devices like, say, a hard drive. Now, as we mentioned, the instructions which the CPU executes are binary codes. They're just a series of zeros and ones. Or more accurately, they're a series of electrical impulses in one of two states, and we represent these states with the symbols 0 and 1. The obvious problem is that these binary codes are extremely unfriendly for humans. Humans just aren't very good at reading and writing a long series of zeros and ones. Writing a program as a bunch of zeros and ones would be extremely tedious. The solution to this problem is to create programming languages. In a programming language, the programmer writes code in a form that's more human-friendly. It's of course not a human language like English, but rather a formal language with formal rules specifying exactly how the code must be written to be understood by the machine. The computer, however, cannot directly execute such code because the code is written as a bunch of text instead of binary instructions. So the text written by the programmer has to be translated into binary instructions, an actual runnable program. Programs which do this translation are called compilers and interpreters. The distinction between compilers and interpreters we'll discuss in a later video. For now, we'll just use the generic term translator. Now, you might be wondering where translators come from. Well, of course, originally people had to write these translators in machine code directly, but once translators existed, people could use them to write subsequent translators.
I like it.
Writing is so important because that's literally how you represent yourself. Through emails, internship, and any of your schoolwork.
So now that you hopefully have a concept of what a programming language is, we can introduce an elementary programming language. This language is in fact one I myself made up, and I call it Pigeon. I created Pigeon explicitly for educational purposes by making it as reductively simple as I believe possible. This doesn't mean, however, that Pigeon is unrepresentative of real programming languages. All of the concepts you'll learn with Pigeon directly correlate to the most essential features of real programming languages. When we write code in a programming language, we write it as text, and this code is called the source code, so called because it's the source from which the translator produces actual runnable programs. The first rule to learn about Pigeon code is that the hash sign, sometimes called the octothorpe or the number sign, that denotes the beginning of a comment. A comment in source code is simply text which is ignored by the translator. All languages allow for comments so that programmers can write notes in code that describe anything about the code which isn't apparent to a human reader. Notice that when I show a comment, I'll highlight it in orange so that you can more easily distinguish it from actual code. The term value in programming generically refers to some piece of data. So a number value like the number 3, that's obviously a value, a piece of data. Values in programming, though, may come in many different types, not just numbers. So in Pigeon, for example, we have numbers, we have what are called strings, we have what are called booleans, and later on we'll introduce a couple of additional types. A string, quite simply, is a piece of text. It's a sequence of text characters. So same code you wish to store someone's name. That name would be stored as a string value. The boolean data type actually has just two different possible values, the values true and false. Booleans come in handy for situations like, say, your program has options that can be enabled or disabled. The enabled state would be represented by the boolean value true, while the disabled state would be represented by the value false. If you're wondering about the odd name, booleans are named after the 19th century English mathematician George Boole, who invented binary algebra, the algebra of logic. So it makes sense that we name the data type for true and false after him. In the text of our source code, when we express a specific value, that is a literal. It is a value literally written in text. So for example, when you write a number in Pigeon, it can just be a simple positive number, like here 3, or a negative number, like say negative 724, or a number with a fractional component, a decimal point, 8.93, or a negative number with a decimal point, like negative 0.888881.
Ah, I realized something I want to change. Okay. I'm gonna change the what was it called? I'm gonna change the overlay. That looks good. The stream elements. Get started. Stream to overlay. Which one is this one? Na 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 na. What in the world? I'm trying to pick a color, but apparently they're all slightly different. How is that even possible? Ugh. Okay. I guess it works for me. I don't like it. How did I know this? How did I know that? How did I know anything at all? Why something? Back up. Oh, I didn't know I can do that. Okay. Okay. And then let's go back to how do I upload something? Oh, Stream tool charity static. Oh, static. That's what. Wait a moment. Keep having a hiccup today. All files. Huh? Oh, upload. I didn't upload anything. That makes sense. Okay, come over here. Let me get this file. Upload it. Okay, good. Yeah, that's what I want. Gimme, 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 gimme. No! It doesn't do what I wanted to do! Ew. Eh. Fine. And then another one. Bum ba-dum bum. Ba-bum bum. Bum 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 bum. Bum 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 bum. Static. Custom. Image. Set image. Upload image. Go back to download photo. Grab photo. Upload photo. Good one. Delete. Submit. Okay. This doesn't get any bigger though. What is that? Hmm. 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 I don't get it. What's next? Hold on, I want to try something. Yep. I don't remember how to do it. Ah! I'll do it later.
When we express Boolean values as literals, we write them simply in lowercase, true and false.
Later.
When we write a string, we enclose the characters of the string between double quote marks. So here the top example, that's a string containing the sequence of characters starting with a capital R, then period, then space, then capital N, lowercase I, lowercase x, O, N. So one thing to note here is that uppercase letters are different characters than lowercase letters. The uppercase N is a different character than the lowercase n. Also note that a space is a self-defined character. It's part of the data of the string. In the second example from the top, that's a string with just a single character, a capital T. The third string down reads elementary, comma, my dear Watson, and then the last string at the bottom consists of just a single character, a percentage sign. So that's how we write numbers, strings, and booleans. There is, however, one more literal for the special value null. The null value, which you can sort of think of as another data type with just one possible value, is used to represent nothing. It's effectively used as a placeholder, meaning there's nothing here. Note that the null value, like true and false, is always written in all lowercase.
No.
When we write a string literal, there are some characters which can only be included by using what's called an escape sequence. For example, the double quote mark character, you can't simply put that in the middle of a string because the double quote mark character denotes the end of the string. Consequently, to include a double quote mark, we have to escape it, meaning we have to put a backslash in front of it. And that indicates to the language that the following character, the double quote mark in this case, is not meant to denote the end of the string, it's just meant to denote a double quote mark character in the text data. So in the string literal at the top here, the first character of the string is simply a single double quote mark character. The backslash followed by the double quote mark, those two characters together represent an escape sequence. They represent one character in the text data, a double quote mark. In the second string, where we see backslash n, that is an escape sequence representing the new line character. The new line character, as the name implies, is used to denote where a new line should start. So the text in this example reads hello, comma, and then on the next line, world, period. Now, of course, what we see here is written all on one line, but the idea is that a program that renders text should render this text on two successive lines. So just to be clear, in the string data, we have this new line character to indicate the intention that there be a new line there, but it's ultimately up to whatever code renders the string on the screen or printer somewhere. It's up to that code to represent the new lines, to draw the character after the new line on the next line down. In our code, however, we must write string literals always on just one line. We can't continue them onto the subsequent lines, so the opening and closing double quote mark of a string literal will always be on the same line. Finally, in the bottom string, the escape sequence backslash backslash is used to denote just a single backslash character. So the text data of the string actually reads c colon backslash blah backslash blah backslash blah. The reason we have to use an escape sequence to denote a backslash character is because the backslash character itself is used to denote the start of escape sequences. So if we just wrote single backslashes here, then the backslashes would appear to the language to denote the start of escape sequences. But that's not what we intend here, so we write a pair of backslashes just to have a single backslash character.
Just one more screenshot, and this SOP is finally done.
So P.
The basic units of action in our code are called operations. And just like in mathematics, an operation is something which takes input values and then returns an output value. Like say, an addition operation where the inputs 3 and 5 returns the value 8. In an operation, the part which specifies which operation to perform is called the operator. Like say, the plus sign in an addition operation, that's the operator. The input values to the operation, those are called the operands. So here's an example addition operation as you're used to seeing it in mathematical notation. The plus sign is the operator, and the operands are 3 and 5. In Pigeon, however, we use a slightly different style of notation for operations called prefix notation. The notation you're familiar with from mathematics is called infix notation, so called because the operator is infixed between the operands. In prefix notation, the operator is placed in front, and then the operands are listed afterwards. Another change we make in Pigeon is that the operators of common operations are not denoted by symbols, but instead are denoted by words. For example, the addition operator is not the plus sign, but rather the word add. So rather than writing 3 plus sign 5, you would write add 3, 5. One other important change with this notation style is that the parentheses that surround an operation are not optional. Every operation is always surrounded in its own pair of parentheses. In infix notation, the parentheses are often optional, like say we can write 3 plus 5 without. Any surrounding parentheses. Now, one advantage of prefix notation is that operators are not limited to having just two operands as they are in infix notation. So whereas in infix notation we have to write 3 plus 5 plus negative 7 plus 11 to add all those numbers together, in prefix notation we can simply write one addition operator followed by all 4 operands. Another advantage of prefix notation is that we never have to worry about precedence. With infix notation, the operators are given an order of precedence, that is, a set of rules that determine which operations are performed before others when parentheses don't explicitly denote the order. So here, for example, when you write 11 minus 2 times 3, the multiplication operation is performed first because the multiplication operator has a higher precedence than the subtraction operator. Really, the only point of this order of precedence is that it often spares us from having to explicitly surround our. Another advantage of prefix notation is that we never have to worry about precedence. With infix notation, the operators are given an order of precedence, that is, a set of rules that determine which operations are performed before others when parentheses don't explicitly denote the order. So here, for example, when you write 11 minus 2 times 3, the multiplication operation is performed first because the multiplication operator has a higher precedence than the subtraction operator. Really, the only point of this order of precedence is that it often spares us from having to explicitly surround our operations in parentheses. We only need to use parentheses in infix notation when we wish to subvert the normal order of precedence as we do here, where we put the subtraction operation in parentheses such that it is performed first before the multiplication. In prefix notation, though, there's no concept of an order of precedence. We just always explicitly put every operation in a pair of parentheses, and there's never a question of which operation is done first. Here, for example, you see the prefix equivalent, where we have a multiplication operator with 2 operands, one of which is the number 3, the other of which is another operation, the subtraction of 2 from 11. Last thing to note here, with some operations like multiplication and addition, the order of the operands doesn't matter, but with other operations like subtraction, it does. For instance, sub 11, 12, that returns 9, but if we wrote sub 2, 11, that would return negative 9. In programming, what we call variables are really quite different from what we call variables in mathematics. In mathematics, variables are used in equations such that the value of a variable possibly depends upon the value of other variables. Like say in the equation x equals 2y, x represents the whole range of possible values for some given y value. A variable in programming, in contrast, always just has one value at any moment in time. A variable is simply a symbolic name which we give a designated value, but we call them variables because over the course of time as the program executes, we can change a variable's value. Over the course of a program, a variable's value may change, it may vary, hence the name variable. Effectively, what a variable represents in the machine is a location in memory to store a value, a location we've given a symbolic name. The jargon term for a name in source code, such as the name of a variable, is identifier. Unlike in mathematics, it's generally considered bad practice to overly use single-letter variable names in programming. Identifiers, though, must conform to a few rules. They can consist of uppercase and lowercase letters, and they can also have numerals in them. However, they cannot have spaces in them, and they cannot begin with a numeral. So these 3 examples are all valid identifiers, but these other 3 are not. The top one here, New York, is not valid because you cannot have spaces in your identifiers. The second one is invalid because you cannot have symbols like the caret sign, the dollar sign, or the asterisk. And the one here, New York, is not valid because you cannot have spaces in your identifiers. The second one is invalid because you cannot have symbols like the caret sign, the dollar sign, or the asterisk. And 43 ASDF, that is not valid because while identifiers may contain numerals, they cannot begin with numerals, they must begin with a letter. The last rule to keep in mind about identifiers in Pigeon is that they are case sensitive, meaning that the case of each letter matters. So if you have an identifier New York where N is capitalized and Y is capitalized, but the other letters are lowercase, that is a different identifier than New York with all the letters lowercase, or all letters of York in uppercase, or some other mix of uppercase and lowercase letters. So all of these identifiers here are considered by the language to be totally different identifiers. If you have a variable named New York in all lowercase, you can also have at the same time a variable named New York in all uppercase, and they would be considered totally separate variables. It turns out that most popular languages, with only 1 or 2 exceptions, have case-sensitive identifiers. The reason case sensitivity is the norm is that it encourages programmers to be consistent. What tends to happen when a language is not case sensitive is that the same identifier written throughout code ends up getting written several different ways, and most people feel that's bad style. It makes the code ugly and hard to read. On the other hand, even though the language allows you to have, say, New York all lowercase and also New York all uppercase, it's generally a bad
Was
idea.
it the
You generally shouldn't be creating identifiers
language
that are just like other identifiers in your code except for the letter case,
guideline?
because doing so easily leads to confusion and
I think
errors.
so. I forgot the name already.
A reserved word is an identifier that is specially reserved by the language. That is, you're not allowed to use that word for your own identifiers. Pigeon has only a couple dozen reserved words. You've seen a few of them already. The operators add, sub, mul. There's also div for the division operation, and shortly we'll introduce a few more.
My work is easy because I use ClickUp. Here's how I keep track of all my tasks. I start by brain dumping everything I need to get done in a list view.
When we give a variable a value, that's called an assignment. To perform an assignment in Pigeon, we write the reserved word as, followed by the name of the variable, and then the value to assign to that variable. So here, for example, in the top line, we are assigning the value true to a variable named dog, and in the next line, we're assigning the value negative 87.2 to a variable named newt, and then the value null to a variable named bird, and lastly, a string with the text rubber baby buggy bumper, we're assigning that to a variable named cat. So now, let's look at our first actual sequence of code. As bar 19 assigns the number value 19 to a variable named bar, and then in the next line, as foo bar assigns the current value of bar to a variable named foo. So foo also now has the value 19. And then in the next line, as bar 3 assigns the value 3 to the variable bar, and in the final line, the value returned by the add operation is assigned to fizz. This add operation returns the sum of 11 and the current value of foo. So what is the current value of foo? Well, it's whatever we last assigned to it, and foo was last assigned to 19, so we sum 11 and 19, returning 30, which is then assigned to fizz. So that's the key concept here. When we use a variable, it has the value of whatever was last assigned to it. This can be a confusing point if you learn programming starting with some other languages, because in most popular languages, assignment is denoted with an equal sign. So instead of writing as foo bar, you would write foo equal sign bar. And this gives many students the false impression that what assignment does is somehow create an equation. That assignment creates a persisting relationship between the two variables rather than just give the target of the assignment the current value of the other variable. And so here in this case, that misconception would lead you to believe that when we assign 3 to bar, that we are also affecting foo and giving it the value 3 as well. But that's not how assignment works. When we assign to bar, it's just assigning to that variable, not any others. Foo still retains the value 19 because that's the last value which we assign to it. In fact, that's how assignment works in all languages, even in languages that misleadingly use an equal sign to denote assignment. Like in mathematics, we use the term expression to refer to anything which evaluates into a value. So an expression in code may be a literal, like null, or the string here, a low, or it may be a variable, because a variable evaluates into whatever value was last assigned to it. Or an expression may be an operation, because operations return values, like say the add operation here will return the sum of 4 and foo. Note that an operation is a kind of expression which itself contains other expressions. So in the add operation here, the variable foo, that itself is an expression, and the number little 4, that itself is an expression. These expressions made up of other expressions we sometimes call complex expressions, in contrast to simple expressions. Another important jargon term is statement. Statement is just a generic term for the units of syntax that make up our code, somewhat analogous to sentences in English. Our code is a series of statements. So far we've seen two kinds of statements, assignment statements and expression statements. An assignment statement, as we've seen, begins with the as reserved word, and an expression statement consists of just an expression, usually an operation to perform some action. So here, for example, as foo 53, that's an assignment statement, and then the next line, the addition operation, is an expression statement. Now, be clear that this is an unrealistic example of an expression statement because an addition operation by itself doesn't do anything useful. It just produces a new number value which doesn't get used, so this statement here is effectively pointless. Let's introduce two operators for which it actually makes sense to invoke them as standalone expression statements. The first of these operators is print. A print operation takes one operand and displays its value as text in a console window. If you're not familiar with the concept, consoles, also called terminals, are the simplest.
Hey, I think that did not fully get processed. I'm gonna have to rewatch this part. Assignment. Have I learned about expression before? Have I? I don't remember. Oh, I think it was YouTube crashed. That makes sense.
In this case, that misconception would lead you to believe that when we assign 3 to bar, that we are also affecting foo and giving it the value 3 as well. But that's not how assignment works. When we assign to bar, it's just assigning to that variable, not any others. Foo still retains the value 19 because that's the last value which we assign to it. In fact, that's how assignment works in all languages, even in languages that misleadingly use an equal sign to denote assignment. Like in mathematics, we use the term expression to refer to anything which evaluates into a value. So an expression in code may be a literal, like null, or the string here, hello, or it may be a variable, because a variable evaluates into whatever value was last assigned to it. Or an expression may be an operation, because operations return values, like say the add operation here will return the sum of 4 and foo. Note that an operation is a kind of expression which itself contains other expressions. So in the add operation here, the variable foo, that itself is an expression, and the number little 4, that itself is an expression. These expressions made up of other expressions we sometimes call complex expressions, in contrast to simple expressions.
Okay, great. Wait, were you even listening? You haven't taken a single note this entire.
Another important jargon term is statement. Statement is just a generic term for the units of syntax that make up our code, somewhat analogous to sentences in English. Our code is a series of statements. So far we've seen two kinds of statements, assignment statements and expression statements. An assignment statement, as we've seen, begins with the as reserved word, and an expression statement consists of just an expression, usually an operation to perform some action. So here, for example, as foo 53, that's an assignment statement, and then the next line, the addition operation, is an expression statement. Now, be clear that this is an unrealistic example of an expression statement because an addition operation by itself doesn't do anything useful. It just produces a new number value which doesn't get used, so this statement here is effectively pointless. Let's introduce two operators for which it actually makes sense to invoke them as standalone expression statements. The first of these operators is print. A print operation takes one operand and displays its value as text in a console window.
Oh wait, I have to download Anki. Hold on. This stuff. Download Anki. I was supposed to make a flashcard and I forgot.
If you're not familiar with the concept, consoles, also called terminals, are the simplest possible way for programs in modern operating systems to display text output and get keyboard input from the user. We'll discuss consoles in detail in a later unit. In any case, here in this code, the first line print with the string waka waka will display waka waka on the console. The second line assigns the value 19 to a variable bar, and then in the last line, we print the value of bar, which at this moment is 19, so the value 19 is displayed on the console. The prompt operator gives keyboard input which the user types at the console. When prompt is invoked, the program waits while the user types at the console, and then when the user hits enter, everything they've typed is returned as a string by the prompt operation. So here in the first line, we invoke prompt, the user types at the console, hits enter, the prompt operation returns that text as a string, and that string is assigned to the variable foo. Then in the next line, if we print values, like say the add operation here will return the current value of the other variable. And so here in this case, that misconception would lead you to believe that when we assign 3 to bar, that we are also affecting foo and giving it the value 3 as well. But that's not how assignment works. When we assign to bar, it's just assigned to that variable, not any others. Foo still retains the value 19 because that's the last value which we assign to it. In fact, that's how assignment works in all languages, even in languages that misleadingly use an equal sign to denote assignment. Like in mathematics, we use the term expression to refer to anything which evaluates into a value. So an expression in code may be a literal, like null, or the string here, hello, or it may be a variable, because a variable evaluates into whatever value was last assigned to it. Or an expression may be an operation, because operations return values, like say the add operation here will return the sum of 4 and foo. Note that an operation is a kind of expression which itself contains other expressions. So in the add operation here, the variable foo, that itself is an expression, and the number literal 4, that itself is an expression. These expressions made up of other expressions we sometimes call complex expressions, in contrast to simple expressions. Another important jargon term is statement. Statement is just a generic term for the units of syntax that make up our code, somewhat analogous to sentences in English. Our code is a series of statements. So far we've seen 2 kinds of statements, assignment statements and expression statements. An assignment statement, as we've seen, begins with the as reserved word, and an expression statement consists of just an expression, usually an operation to perform some action. So here for example, as foo 53, that's an assignment statement, and then the next line, the addition operation, is an expression statement. Now be clear that this is an unrealistic example of an expression statement because an addition operation by itself doesn't do anything useful. It just produces a new number value which doesn't get used, so the statement here is effectively pointless. Let's introduce 2 operators for which it actually makes sense to invoke them as standalone expression statements. The first of these operators is print. A print operation takes one operand and displays its value as text in a console window. If you're not familiar with the concept, consoles, also called terminals, are the simplest possible way for programs in modern operating systems to display text output and get keyboard input from the user. We'll discuss consoles in detail in a later unit. In any case, here in this code, the first line print with the string waka waka will display waka waka on the console. The second line assigns the value 19 to a variable bar, and then in the last line, we print the value of bar, which at this moment is 19, so the value 19 is displayed on the console. The prompt operator gets keyboard input which the user types at the console. When prompt is invoked, the program waits while the user types at the console, and then when the user hits enter, everything they've typed is returned as a string by the prompt operation. So here in the first line, we invoke prompt, the user types at the console, hits enter, the prompt operation returns that text as a string, and that string is assigned to the variable foo. Then in the next line, if we print foo, that same string is displayed on the console. Effectively, whatever the user types is repeated back to them. For the sake of simplicity, print and prompt are going to be the only means we have in Pigeon to perform input and output. We'll have no other way to put something on screen or get input from the user. This is not because of anything fundamentally limited about Pigeon, where Pigeon developed into an actual language would be perfectly capable of doing any input and output, but for educational purposes we're keeping things simple. Ultimately, doing anything interesting in code of course relies upon things like storing data in files, drawing on the screen, getting mouse input, and so forth, but you should accept now that in this course we'll be going through hours of material before we do any of those things. You're going to have to trust me that this approach is both easier and in the long run more efficient, and will give you a better understanding of how programming actually works than a flashier approach would. Starting with graphics programming, for example, just makes things more confusing because that approach inevitably requires glossing over fundamental concepts. You'll get the thrill of seeing your code do something flashy, but you won't really understand how you did it.
Imagine being able to build an app with
Imagine that I'm not listening to an ad. Bring idea to life.
Print operator, we can write our first program, which is the traditional first program students always write, called Hello World, a program which simply prints on the screen the text Hello World. In Pigeon, this program is exceedingly simple. It consists of just one statement, a print operation with the string Hello World. In some other languages, though, Hello World can actually be surprisingly complicated. To begin to do more interesting things in code, we need yet more operators. First off, the EQ operator performs an equality test on 2 or more operands. When all the operands have the same value, EQ returns the Boolean value true, but otherwise returns false. So here the first 2 examples return true, but the last example returns false because 6 is not equal to 2. The not operator takes a single Boolean value and returns the reverse truth value, so not true returns false and not false returns true. These 2 operators, EQ and not, come in useful for what we can call conditional execution. When we write code, we often want a section of code that is executed only conditionally. That is, depending upon some condition, the block is either executed or skipped over. For this purpose, we have in Pigeon the if statement. An if statement is written beginning with the reserved word if, followed by a condition, and then on the following lines we write what is called the body. The body consists of one or more other statements, but these statements are written indented under the if. The way the if works is that the condition, which is some expression returning the Boolean value, is evaluated, and if that condition returns true, then the body is executed. Otherwise, if the condition returns false, the body is skipped over. So that's why it's called if. It has a sense of, if this condition is true, then do this stuff, otherwise skip over this stuff. Here in this example, we have an if where the condition is the expression EQ x3, and the body consists of 2 statements, the first printing cat and the second printing dog. So when this code executes, if the equality operator returns true because x does equal 3, then first the code will print cat, then it will print dog, and then execution continues in the line after the if, in this case a line that prints bird. If, on the other hand, x at this point does not equal 3, the equality operation will return false, and so the statements of the if body will get skipped over, so this code will just print bird. Other times in code, we want not just to skip over something, we want to make a choice of either doing one thing or another thing, and this is called mutual exclusion. We do one thing or the other, but not both. For this purpose, we can simply use 2 separate if statements by giving them logically inverse conditions. So when this example executes when x equals 3, the condition of the first will be true, but the condition of the second will be false, so the code will print high, but not by. On the other hand, when x does not equal 3, then the condition of the first will test false, but the condition of the second if will test true, so this code will print by, but not high. Because mutual exclusion is used very commonly, rather than having to write two separate if statements, we have a special convenience, the else clause. An if statement can be followed by an optional else clause, which begins with a reserved word else and has its own body. When the if statement is executed and the condition is true, the first body is executed, but the body of the else is not. Conversely, when the condition tests false, the body of the else is executed, but the first body is not. So for example here, when the condition is tested and x does equal 3, then this code prints high, otherwise when x does not equal 3, it prints pi. Now in some cases, you might wish to have mutual exclusion between more than just two cases. You might have three cases as we have here. In this example, again when the condition tests true, we execute just the body of the if, otherwise we execute the body of the else. But this else body itself contains another if statement, so when the else executes, the condition of the if statement is tested, and if true, then it prints pi, otherwise not. Effectively, we have three mutually exclusive cases here. When x equals 3, the code prints high, when x equals 5, it prints pi, but when x doesn't equal 3 or 5, then nothing happens. To make it easier to write such cases, we can have clauses beginning with a reserved word elif, which is a contraction of else and if. Elif clauses effectively combine an else with an if. When you see an if with an elif clause, as usual, the condition of the if is tested, and when it's true, then the first body is executed, but when false, then we test the condition of the elif, and when that is true, we execute the body of the elif. Otherwise, we skip over that body as well. So we can rewrite the previous example with an elif like so. We can actually give an if more than one elif clause, effectively adding on more mutually exclusive cases. So here in this example, as usual, we start at the top and test the condition of the if itself, and when it's true, we print high and then skip over all the elif clauses. Otherwise, we test the condition of the first elif clause, and when that's true, we execute its body. Otherwise, we test the condition of the next elif, and so forth. So in short, the way this works is that the conditions are tested from top to bottom, and the first one that tests true, its body is the one and only one to execute. In the case that none of the conditions test true, then all the bodies get skipped over. So we effectively have 5 mutually exclusive cases. When x equals 3, we print high. When x equals 5, we print pi. When x equals -7, we print mu. When x equals 14, we print woof. And when x doesn't equal any of those values, we don't print anything because we've skipped over the bodies of each clause. When an if does have one or more elif clauses, it can also end with an else clause. The else clause effectively acts as the default, such that when none of the conditions test true, it's the else clause which gets executed. So here, when x doesn't equal 3 or 5 or -7, the code prints meow.
As a medical student,
To have more interesting condition expressions, we need a few more operators. First, there's the less than operator, which returns true when its operands, which all must be numbers, increase in value from left to right. So the first example here returns true because 25 is less than 76, and 76 is less than 8,000. But then the second example returns false because 35 is not less than -2, and the third example also returns false because 2 is not less than 2. A similar operator is less than or equal, which we write LTE. In the last example here, when we write LTE 227, that returns true because 2 is less than or equal to 2. And then, as you might imagine, we have the reverse of less than, we have greater than, which returns true when its operands decrease in value from left to right. So the first example here, GT 25, 76, 8000, returns false because 25 is not greater than 76, nor are they greater than 8000. And the second example returns true because 35 is greater than -2, which in turn is greater than -10. And the last example returns false because, yes, 8 is greater than 4, but 4 is not greater than 4. If we use the greater than or equal operator instead, written GTE, then this last example returns true because 8 is greater than 4 and 4 is equal to 4. The AND operator takes 2 or more Boolean operands and returns true only when all of those Boolean values are true. So the first example here returns true, but all the remaining examples return false. The OR operator also takes 2 or more Boolean operands, but returns true when just at least one of the operands is true, not necessarily all. So the first 3 of these examples return true because at least one of the operands is true or all of them are true, but then the last example returns false because the operands are all false. The modulus operator, written mod, returns the remainder of division. So for example, mod 15/5, 15 divided by 5 is 3 with the remainder 0, so this returns 0, but 16 divided by 5 is 3 with the remainder of 1, so 16 mod 3 returns 1. And mod 17/5 returns true because 17 divided by 5 is 3 with the remainder of 2. One useful thing to do with a mod operator is to test whether a number is even or odd. Here when we write mod x2, when x is an even number, mod x2 will return 0. So here in this code, when x is even, mod x2 returns 0, and yes, 0 is equal to 0, so the condition of the if is true, and the code prints even. Otherwise, when x is odd, mod x2 will return 1, and 1 is not equal to 0, so the condition will test false, and the code prints odd. Often in code, we want what's called a loop. That is, we want a section of code that repeats some number of times. For this purpose, we have the while statement. A while statement looks very much like an if, with a condition and a body, but with a reserved word while in place of if. The word while was chosen because a while loop has a sense of do this stuff while this condition is true. The way while works is that, just like an if, the condition is evaluated, and when it's true, the body is executed. The difference is that once the body is done executing, the condition is tested again, and when the condition is once again true, the body is executed again. This happens ad infinitum until the condition tests false, at which point the body is skipped over, and execution continues on past the while. So consider what this code does. First we assign 6 to a variable named z, and then we encounter a while loop where the condition asks, is z greater than 0? Currently z has the value 6, so yes, it is greater than 0, so this returns true, and we execute the body, which prints the value of z, which is currently 6, and then assigns to z the value of z minus 1. Z minus 1 is 5, so we assign 5 to z. And now that the run through the while body is finished, the condition is tested again, and the value of z is still greater than 0, so the body is executed again, the value 5 gets printed, and z is assigned 1 less than 5, the value 4, before the condition is tested again. And this process continues like this until, in the last iteration of the loop, z is assigned 0, and so the condition will test false because 0 is not greater than 0, ending execution of the loop. In effect, this code ends up printing the value 6, then 5, then 4, then 3, then 2, then 1. The body of this loop ends up running 6 times. Now that we've introduced loops, we can write another traditional simple program called fizzbuzz. The fizzbuzz program simply prints all the integers from 1 to 100, except instead of any integer evenly divisible by 3, the program prints fizz, and except for any integer evenly divisible by 5, it prints buzz. And then for any integer evenly divisible by both 3 and 5, the program prints fizzbuzz. To start, we know we're going to be printing a range of numbers from 1 up to 100. So first we're going to find a loop in which a variable starts with the value 1 and gets incremented each iteration until, in the last iteration, it has the value 100. So here the variable x is given the initial value 1, and then the loop tests whether or not x is less than or equal to 100, and so every time this condition tests true, the body of the while loop will execute for another iteration. At the end of the body, we increment the value of x. We take the current value of x, add 1, and then assign the result to x itself. So what we have here is a loop which in the first iteration, x has the value 1, in the second iteration, x has the value 2, in the third iteration, x has the value 3, and so forth until in the last iteration, x will have the value 100, which then will get incremented to 101, and so the condition will then test false because 101 is not less than or equal to 100. Now, in each iteration of the loop, we're going to need to determine whether the value of x is equally divisible by 3 and whether it is equally divisible by 5. When a number is equally divisible by 3, the modulus of that number by 3 will be 0, so we do mod x3 and test whether that is equal to 0. That will assign true or false to the variable by 3. And then we do the same for 5, taking the modulus of x by 5, testing whether the result is equal to 0, and assigning the true or false value to by 5. Based upon these two variables, we then need to decide which thing to print among 4 mutually exclusive cases. When both by 3 and by 5 are true, that means that x is evenly divisible by both 3 and 5, so we print fizzbuzz. In the case where x is divisible by 3 but not by 5, we print fizz, and in the case where x is divisible by 5 but not by 3, we print buzz. Lastly, in the case where x is not divisible by either 3 or 5, we print the value of x itself.
We made
So that's the entirety of the FizzBuzz program. It
cell
prints all the numbers from 1 to 100,
equals
except when the number is evenly divisible by 3 and 5, it prints FizzBuzz instead, and when the number is evenly divisible by just 3, it prints Fizz, and when the number is evenly divisible by just 5, it prints Buzz. A very important thing to note here is that the ordering of the mutually exclusive cases matters in this example. Given how we wrote our conditions, our second and third cases test
Divisible by both, you say Fizz plus. Only by 3. Fizz. Only by 5. Where else? Print the number.
is evenly divisible by 3 and 5, it prints FizzBuzz instead, and when the number is evenly divisible by just 3, it prints Fizz, and when the number is evenly divisible by just 5, it prints Buzz. A very important thing to note here is that the ordering of the mutually exclusive cases matters in this example. Given how we wrote our conditions, our second and third cases test true when the first case tests true, because of course when both by 3 and by 5 are true at the same time, by 3 and by 5 are true individually. So if we reorder these cases, we can get the wrong behavior. For example, if we put the case of just by 3 is true first, then we print Fizz when we're supposed to print FizzBuzz, because the just by 3 case would test true when both by 3 and by 5 are true. Likewise, if we put the case of just by 5 is true before the case of by 3 and by 5, then we print Buzz when we're supposed to print FizzBuzz. One way to think about this is that our case conditions have been partly left implicit by their order. In an if statement with elif clauses, the condition of the elif clauses implicitly require that all previous conditions test false. So in our original ordering, when we put the condition of by 3 and by 5 first, the second condition by 3 implicitly requires that the condition by 3 and by 5 tested false. If we wanted to keep the same logic but write these clauses in reverse order, we'd have to change the condition from just by 3 to by 3 and not by 5. So the lesson is, when writing your mutually exclusive cases, be sure to either fully state the conditions or simply be cognizant of what's being left implied in their order.
Scribe makes step-by-step guides for any process with AI. You know what's terrifying at work? When you start a new job and there's
Rather than just use the operations predefined in the language, programmers also define their own operations, called functions. Functions are also sometimes called routines, subroutines, procedures, or in some contexts, methods. Function, though, is the most common term. Once the programmer has defined a function and given it a name, they can invoke, or call as we say, that function just like they invoke one of the built-in operations. In parentheses, write the name of the function, followed by however many operands are expected by the function. To create a function in Pigeon, we use a function statement, beginning with a zero-word function. That's followed by the name you choose for the function, an identifier, and after that parameters, which we'll explain in a moment, and then indented on the following lines, you write the body, a series of statements that execute when the function is invoked. So here, for example, we create a very simple function called Eric. This function Eric has no parameters, and it just has one statement in its body, print hello. So having created this function, we can then invoke it by simply putting its name in parentheses. And because it takes no operands, we just write the function name in parentheses, and that's it. When we invoke this function Eric, all it does is print hello. Now functions, like operations, can take input values, but rather than calling those input values operands, we usually call them arguments. And when we invoke a function, the arguments are passed to parameters, which are variables in the function that receive the input values. So here, for example, we create a function we call Ryan, and we give it two parameters, the first called bat, and the second called goat. Then in the body of this function, what we'll do is subtract the value of bat from goat and print the resulting value. So if we then invoke the function,
variable which receive value.
parameters, which are variables in the function that receive the input values. So here, for example, we create a function we call Ryan, and we give it two parameters, the first called bat, and the second called goat. Then in the body of this function, what we'll do is subtract the value of bat from goat and print the resulting value. So if we then invoke the function with the arguments 4 and -9, the value 4 gets passed to the parameter bat, and the value -9 gets passed to the parameter goat. And so in the first invocation of this function, when we subtract bat from goat, 4 from -9, we get -13, and the function will print -13. In the second invocation of Ryan here, the argument 3 is passed to bat, and the argument 5 is passed to goat. So when we subtract bat from goat, we get 2, and so the function prints the value 2. Operations can not only take input values, they can return an output value. To return an output value, we use a return statement. Here, for example, is a function Jerry, which simply returns the value 3. When we invoke Jerry here, it returns the value 3, and so this code prints 3. Now let's write a function that might actually be useful, a function that computes and returns a factorial. In case you don't recall, a factorial of a number takes that number and multiplies it by all integers down to 1. So the factorial of 3, for example, is 3 times 2 times 1. The factorial of 0, however, is a special case which always returns 1. So here's one way we could write a factorial function in Pigeon. Let's call the function factorial and give it a single parameter named n. In the body, we use a loop to compute the factorial and store the result in the variable val, which is then returned in the last statement of the body. So if we call the factorial function with the argument 4, it'll return 24 because 4 times 3 times 2 times 1 is 24, and then if we call the function with the argument 5, it'll return 120 because 5 times 4 times 3 times 2 times 1 is 120. Let's step through exactly what goes on when the argument is 4. The parameter n starts with the value 4, and then we assign to the variable val the number 1. Then we enter the loop if n is greater than 0 and n is currently 4, so the condition tests true. In the loop, we multiply n times val, that's 1 times 4 yielding 4, which we assign to val. Then we decrement n by subtracting 1 from n, yielding 3, and assigning the result to n. So when we test the condition again, is n greater than 1? Well, yes, because 3 is greater than.
Hold on. Change the name of the site. Then also need to type secure as well. Add tab to big cybersecurity. Have a crash course? Yes. Move it here. Here. As included. Oh, that's Google. $2 is not even possible for a certificate. I don't know how to use it. Why would that be so long? Morning. Just before we get to do it. I don't want. Ah, it's frozen again. Whoop. I'll just wait.